Hello, this is Ariel Martinez, and this is my lab report for Lab 3, Black Hole, for Physics 2211. So today I'll be giving a small introduction to the lab, discuss the lab procedure, the initial conditions of the lab. I'll discuss my code and my graph, and then what it means, and then some possible what-if questions. So for this lab, we are generating a unique star trajectory around the black hole through a VPython simulation. So knowing the star's mass and unique trajectory, which were given to us, our goal is to find the net force on the star because of the black hole, and then to estimate the mass of this black hole. The only force felt by the star is the force due to gravity from the black hole. This is something that's given to us from the problem set. And for this lab, we'll be using the centripetal force calculations and the gravitational force, where Fg is equal to the gravitational constant g, the mass of one object times the mass of the other object, divided by their radius squared. So the procedure for this lab, so there's really no real procedure for this lab to collect data, since it's not really possible for us to analyze the star trajectory in the black hole. So instead, we're going to be using simulations based on the conditions given to us, and based for a star trajectory using a VPython simulation, and then analyzing that data to draw conclusions such as the net force on the star and the black hole's mass. So some initial conditions that were used for this lab. So we know the gravitational constant g is equal to 6.7 times 10 to the negative 11. And then we were told that the star's mass is 2 times 10 to the 30th kilograms, and the time interval is 1 day, so 60 times 60 times 24 seconds, and then the initial observation happens at t equals 0. And so this is a screenshot of my code. So for the while loop to iteratively generate the star's trajectory, and so we have the initial velocity and the final velocity, which were calculated previously, and it was given to us, and the initial momentum is the star's mass times the initial velocity, and the final momentum is the star's mass times its final velocity. And then delta V and delta P were calculated as shown. So the x component of delta V is V final minus V initial in the x component. The y component is V final minus V initial in the y component, and the same thing for the momentum. Then to calculate dp dt, which is the rate of change of momentum, it's delta P over delta T. And then the net force is just equal to dp dt, and based on Newton's second law. And then we have to calculate the parallel component of momentum. So first we calculate p hat, which is the magnitude of momentum divided by, which is the momentum vector divided by its magnitude. Then we get the magnitude of momentum in order to calculate the parallel component of dp dt, which is just p hat times the magnitude of momentum. And then this dp dt parallel is equal to the F net parallel based on Newton's second law. Then we calculate the perpendicular component of the rate of change of momentum, which is just the rate of change of momentum minus the parallel component of the rate of change of momentum. And then the perpendicular component of the net force is just equal to the perpendicular component of the rate of change of momentum. And then we calculate the mass of the black hole, as can be shown in the code here, and where the mass of the black hole is equal to the magnitude of the net force times the magnitude of the star squared, divided by the constant g, the gravitational constant, times the mass of the star. Then we just update all the position and graph the forces as shown. So this is a model graph that was generated for me. So this is the star's trajectory. The center is the black hole, and the yellow circle is the star. And then we have the final, so the net force is shown there, and the parallel perpendicular component is shown as well. And then the number above, 1.38 times 10 to the 34, is an average calculation of the mass of the black hole. So what does this all mean? Well, how are the net force and its parallel and perpendicular components different from the rate of change of momentum and its parallel and perpendicular components? So really, the net force and the rate of change of momentum are the same thing. So what's different are the components. So the perpendicular component of the net force and the rate of change of momentum alters the star's direction, whereas the parallel component of these alters the magnitude of the star's velocity. And so what if the black hole, if the black hole the star is orbiting was removed, and a new black hole of unknown mass was placed there instead, and the orbit of the star remained unchanged? So would we be able to tell that this change was implemented? And so to answer this question, so since the star's orbit remains unchanged, that we would not be able to tell that the star was orbiting a different black hole, since the trajectory would be the same, and the mass would probably also be the same of the black hole.